Time dilation. In a spaceship there is a clock consisting of a single photon bouncing back and forth between two mirrors arranged opposite each other. An observer in the spaceship sees the photon bounce directly back and forth between the mirrors, covering a distance c t0. The spaceship has a constant relativistic velocity of v. This means that for an observer outside the spaceship, the pulse of light has to travel further a distance of ct subscript v, where c is the speed of light. The distances ct subscript v, ct subscript 0, and vt subscript v make up a right-angled triangle, and thus we can use Pythagoras' theorem to calculate the factor by which time t subscript v is longer than time t subscript 0. ct subscript v squared equals ct subscript 0 squared plus vt subscript v squared. Rearranging this, we get ct subscript 0 squared equals ct subscript v squared minus vt subscript v squared. Dividing by c squared, we get t subscript 0 squared equals t subscript v squared minus v over c squared t subscript v squared. Therefore, t subscript 0 squared over t subscript v squared equals 1 minus v squared on c squared, or t subscript v equals t subscript o over the square root of 1 minus v squared on c squared. For a stationary observer, time appears to go more slowly in the frame of reference moving with a velocity v, and this is according to the equation t subscript v equals t naught over the square root of 1 minus v squared on c squared. To an observer in the moving frame of reference, time for them appears to pass normally. However, when they look at the stationary observer, who, from their frame of reference, is travelling with a velocity v, time for the stationary observer would appear to run more slowly. Both observers are in fact correct within their frames of reference. This leads to the twin paradox. Imagine a situation where one of two twins travels to a distant star at close to the speed of light, turns around and returns to their home planet, while the other twin remains on the home planet. From the point of view of each twin in their own frame of reference, the other twin is seen to age more slowly. However, it has to be remembered that special relativity only applies to inertial frames of reference, and only the twin who remains on the planet is in an inertial frame of reference. The twin on the spaceship accelerates, then decelerates, turns around, accelerates, and then decelerates during their journey. So as only the twin on the planet is in an inertial frame of reference, their analysis would in fact be correct. To calculate the effects for the space twin, as they are in a non-inertial frame of reference, the general theory of relativity would need to be used, according to which, while the space twin was undergoing acceleration, time for them would run more slowly, thus resolving the paradox. The Hafele and Keating experiment. In 1971, researchers from the US Naval Observatory carried out an experiment to investigate time dilation. 4 cesium atomic clocks were carried twice around the world, once in an easterly direction and once in a westerly direction, on commercial jet aircraft. When they returned and compared their clocks with the clock at the observatory in Washington, D.C., the clocks travelling eastward lost, on average, 59 plus or minus 10 nanoseconds, and those travelling westward gained, on average, 273 plus or minus 7 nanoseconds. This result was in line with the predictions of the theory of special relativity. The researchers concluded that these results provide unambiguous empirical resolution of the famous clock paradox with macroscopic clocks. Time dilation. The formula for time dilation can be derived using Pythagoras' theorem and a thought experiment involving a clock consisting of two mirrors and a single photon. The formula for time dilation is T subscript V equals T subscript 0 over the square root of 1 minus V squared on C squared, where T0 is the time for an observer in the clock frame of reference. T subscript V is the time as seen by an observer moving relative to the clock. V is the velocity of the observer relative to the clock frame of reference, and C is the speed of light in a vacuum. In 1971, researchers from the US Naval Observatory carried out an experiment to test the predictions of the theory of special relativity regarding time dilation. They sent atomic clocks around the world in both easterly and westerly directions. The results from this investigation confirmed the predictions of the theory of special relativity.